Good morning, everyone, and welcome to our webinar, Charging with Solar, How to Integrate EV Fleets with DERs. So we're thrilled to have you with us today. I'm Sam. I'll be your host for this session. We're honored to have Elizabeth Hughes, Sales and Applications Engineer at the Mobility House, Maeve Lawniczak, Project Manager at AlphaStruxure, and Tom Williard, Vice President, Clean Energy at NP5. They're going to share their extensive experiences with working on both public and private sector projects, presenting real-world examples of successful implementations. Our goal is to move beyond the theoretical discussions and provide you with practical, actionable insights that you can apply into your own operations. So thanks again for joining us, and we're going to get started. I'll be handing it over to Elizabeth.
Hi, everyone. My name is Elizabeth Hughes, and I am our Sales and Applications Engineer for the Mobility House in North America. That means I'm our friendly product nerd, and I also help design our sites, especially when there's any complexity or goal in mind, which today you'll find out really is the case often with DER sites. I will be covering some key basic considerations of the coordination of DERs with EV fleets. I will be going through and explaining some concepts today with the goal that it helps you make sure that your sites end up working the way you want them to, and also that the process is as smooth as possible. Now, jumping into things, let's talk about what are DERs. Now, DER stands for Distributed Energy Resource, and I think NREL has a wonderful description of them, so I've put it up on your screen in blue. But the points I want to specifically draw your eyes to today is the part in bold where it says energy generation and storage technologies, and then the second point where it says energy where you need it. And we'll get back to that first point, but I want to dive in a little bit on why is it so important that DERs are energy where you need it for EV fleets. EV fleets are unique when we put them and connect them to the power grid in that they are extremely location-specific load. This is in contrast to, say, residential fleet charging applications. Let's imagine a neighborhood where you have an average amount of EVs increasing throughout the neighborhood. You can imagine a wide cylinder covering that area with its height generally increasing to show how the power requirements of that area are increasing. Now, if we think about specifically an EV fleet charging depot, in contrast, that's a very small and tall cylinder, of course, a large amount of power requirements and a very specific interconnection or address. Putting some real numbers to this, if we take an average transit site that has about 50 buses, doing some quick math, we find out that that transit site is going to require more power than 800 average US homes. Going back to that first point about energy and generation technologies, DERs can be broadly broken down into two sections. Generation, which gets broken down into controlled generation, think your traditional backup generators, or your non-controlled generation. So traditionally solar falls into this category. And I want to make sure that we put a distinction on controlled versus predicted, right? Because solar is heavily dependent on the weather. We can predict the weather, but we cannot control the weather. On the other side, we have controllable storage, and usually we're thinking about battery energy storage systems, or basically large banks of batteries that are installed on site. Usually when we think DERs, we primarily or first start out thinking about how these batteries are going to discharge, but when we're doing system design in general, we also have to make sure our system works when these storage have to act like controllable loads. Now, there are multiple different reasons to connect EVs with DERs, and I have about 4 of them up on my screen, but I will admit you might need a multiple of them, or you might have other reasons entirely. But for these 4, I'll start out with emission reduction. Your company may be looking to have reduction in the CO2 emissions it produces, and so you might want to prioritize emission reduction by, say, prioritizing renewable generation on site. Or you may be a fleet that is considered critical, who needs to keep operating no matter what the power grid does, whether it's up or down. Think critical fleets in like transits or schools or municipals like fire and police, right? They're going to want to try to think about some backup solutions like a backup generator or maybe additional on-site storage. Maybe cost optimization is the most important thing for you. Using your own energy that you create on site can often be cheaper than buying it. This is often called self-consumption. You might also be worried about demand charges or time of use rates that might apply during periods of peak charging that a charge management system can't move. Oftentimes, you're going to want to discharge a battery energy storage system during that time to help mitigate those costs. And finally, for my fourth reason, you might have limited capacity on site. Think back to that really tall cylinder. While there are technologies that can help mitigate that, such as automated load management, hint, hint, go check out our other webinars and blogs on the series, there are times when you're going to need, ALM and DERs to make your site possible. So I've already kind of leaned into this, but what is a charge management system, or CMS? A charge management system controls when and how much power groups of chargers use. When talking charge management systems in the context of DERs, you can think of them like control systems of your chargers, and that they will be the component that will be incorporated into the overall optimization and communication architecture of your site. They're the things that can watch and respond to what the DERs are doing and take orders from a centralized point of intelligence. When designing sites, we often use one of two architectures, the first being a centralized intelligence architecture. This is where one device is making all of the decisions and getting all of the information flow from each of the components. This one device must be able to give directions to each component. This one device is also generally in charge of all the overall optimization. A microgrid controller inside of a microgrid is a commonly thought of example. Now, decentralized intelligence, which is a rarer model to think about, has each component that can either act completely independently, or that it will watch for a certain set of inputs from other components of the system and then act based on those inputs. Because there is not one centralized thing making all of the decisions, planning must be done in order to ensure that the system components react in an appropriate way in all scenarios. An example of this would be a charge management system that is metering a battery energy storage system. Centralized intelligence systems often cost more due to the addition of the centralized intelligence unit, but they can often handle more complex optimizations. Both of these types of systems require significant planning. Now, oftentimes the communication method of a specific integration is going to depend on the type of architecture we just described. Thinking back to that previous example, Modbus, which is a language that is used to talk to microgrid controllers, is often used because there are often multiple PLCs in each of the different DERs. In contrast, meters are a simple way to watch for various power changes on a site caused by the action of other components in a decentralized system. The method of communication also might depend on the reason for the integration. Are we talking about something that has a cloud backend and is not critical for site power functionality? Then an API should be fine for that. But if we need to find a customized solution, this is where a digital signal can allow for a greater flexibility for the specific site purpose. Wrapping this up, we often have different types of stakeholders in a DER and EV project, and they can be separated into three main categories. First, let's talk about our end-use stakeholders. They're the people that in the end will use the site and operate the fleet. They need a firm vision of what's important and in what order. Is resilience number one and cost optimization number two? They also need to be the experts in the room about how their fleet needs to operate in the end. They don't need to know the exact plan, but they need to be able to define the success metrics. For example, a site may need 50 vehicles that run this type of route daily, and that they care about resiliency and then capacity because they have an old building, and then cost. Next, you have your project vendors. They need to be the experts in either their components, think vehicles, DERs, charge management, chargers, or they need to be experts in putting together the pieces at various stages of the process, such as planning, coordination, or installation. All of them should be able to explain how what they do relates to the overall project and be able to work in the gaps between their expertise and another member's expertise. For example, you should be able to ask your charge management provider or your microgrid controller provider, how will the charge management system talk with the microgrid controller? Or you should be able to ask either your planning vendor or your installation vendor, how are we going to make planning such that it makes installation easy? The more experience your project vendors have, the better. Finally, you have your public agencies. Now, while I admit some of your end user stakeholders may be agencies themselves, when I talk about public agencies in this context, I mean the authorities having jurisdiction, the AHJs, which are in charge of permitting, and the utilities, which have their own interconnection requirements and may also be supplying power to the site. These entities are going to have a special eye towards capacity constraints, and they're also a special eye towards the planning and execution of a project. It's important to involve them in the conversation as early as possible. Now, to tie this all together, I've created an imaginary site for you all. We have a customer that has capacity constraints and is also worried about the cost to charge their vehicles. Our end users are first going to go over and give our team the location of the project and also if they have any capacity constraints or what the weather patterns are for the site. The end users are also going to provide them information such as the priorities and the expected duty cycle of the fleet. After that, we, the project team, then get some key KPIs to design towards. Next in our project vendors will coordinate and plan out the site's overall architecture and choose for this specific site a distributed intelligence model due to the limited complexity of the site and to save cost. In this case, they decide to have the charge management system watch and respond using meters to the solar panels. And in addition, they get the added benefit of watching the building load as well. Finally, because of automated load management and the added capacity of the site due to the solar, we are able to stay within the capacity constraints needed by the public agencies while still meeting the fleet's duty cycle. As you can see, paying attention to the key considerations results in a site with a successful DER and EV integration that is tailored to the site-specific needs of the end customer. And with that, I'm going to hand it over to Tom so he can get into even greater detail on some of these points, but thank you so much.
Okay, great. Thanks, Elizabeth. That was really well done. Let's see here. Let me share my screen. So just a quick few words about NV5, the company that I work with. We're a 70-year-old international engineering consulting firm based primarily in the United States. We also have offices in Europe, the Middle East, and in Asia. There are 6 different verticals that we work under: geospatial, environmental health, infrastructure, utility services, building and technology, and construction and quality assurance. I'm in the building and technologies group in the clean energy subvertical there. And we work a lot with the utility services group on these kinds of projects. So NV5, it's a large, like I said, 4,500 person engineering firm, and we can handle just about anything that needs to be done around these projects except construction. So for these particular kinds of like EV and DER projects, we handle everything from early stage market analysis and feasibility all the way through operations and asset management. We support that with project engineering and project management front to back. And that's all done under one roof. So that NV5 can do that whole thing. Okay, so let's jump into this thing. So I wanted to start off with kind of the main message that I wanted to talk about here, which is what makes these fleet transitions a challenge. And it turns out that these things are complicated. And, we've been doing solar PV systems for the last 20 years and battery energy storage for probably the last 15 years and combining those things in microgrids, which gets more and more complex. What we found, though, is that EV transition planning is quite a bit more complex than those things. It's not like a solar project. And there are reasons for that. A lot of it is because it's a new market and it's really a dynamic market. So there are lots of changes happening at once that you have to deal with. So it's like juggling a bunch of balls like a regular project, except those balls are moving a lot. So we've got incentives and tariffs and mandates. All those things are going to be changing during the course of your project. The technology is still emerging. We've had issues with the chargers as well as the vehicles that we've had to manage during these projects. And as Elizabeth was talking about, you need to have a really solid understanding of how you use your resources and what you want to do with them so that we can match routes and chargers and vehicles. And lastly, when you're doing EV charging and EVs, there are humans involved. And this is a new thing in some ways for us. So human behavior actually is an important aspect of this. Okay, so what are we seeing with DERs and EV charging being put together? We see basically two things right now in the market. First one is load shaping, where we are trying to shape the load of the site to the tariffs, the dwell times of the vehicles, the utility requirements. It needs a lot of good data to do this. And in order to shape the load well in complex environments, a CMS like Mobility House is critical for managing that. The other thing we see is that customers are really interested in resiliency. And well, they should be, because everything's been moving towards electricity here. And how do you manage that? So in the past, you had tanks of diesel sitting around and you could keep your buses running. Now you've got electricity. And so that resiliency piece is a real critical aspect of it. It turns out that solar plus battery storage is typically cost prohibitive, is what we've seen. And so there's usually a genset, some sort of more traditional backup associated with these systems as well. So common challenges when we get into these projects. So electricity tariff complexity, the first one. One of the things that we're seeing a lot of is that utilities are now adopting tariffs that are EV specific. And to get to those tariffs, oftentimes you have to put in a separate service or a separate meter or sub-meter to manage that or to get to those tariffs for the EVs. So when you get into figuring out how to manage that, we need to figure out, do you put in that separate meter? Do you design for it now in anticipation of the utility wanting to go in that direction? There's also significant, changes in tariff structures as the PUCs and the utilities out there learn more about this usage and how it impacts their costs. Fuel switching. So, like I mentioned, we're used to having diesel buses or maybe CNG, and you've had that energy stored on site. Now you don't. And so what you're up against now is real-time pricing and locational pricing. And in order to track that, because those prices change, they can be changing real time with time of use rates or even real-time rates. A CMS is really important to make sure that you can track those changes in the cost of energy on a real-time basis and manage that with your fleet charging. Project design changes. Like I mentioned, once we get into the project design, we're seeing all kinds of changes during the design process because incentives, mandates, and technology is changing during that design phase. And so that requires a lot of flexibility and a lot of planning. Future proofing too, since these things are changing so quickly and there are mandates to roll out more of these things. The question we always run into with clients and really work on is how much cost do you put in now to future proof versus costs that you're going to do later? And there's a balancing act there. Often you can put things in cheaper now as one project. And then load management. So CMS is critical for that. And I'll talk a little bit more about that in one of our quick case studies here. And lastly, all of these systems, DERs, even something that's like solar PV, right? No moving parts, people think. What could go wrong? A lot, as it turns out. So all of these systems require maintenance, especially EV charging. So we have human interactions with these systems, and that always makes things a lot more challenging. Okay, so just a couple of quick case studies here. So I'm going to talk about one that we did with a city in Central California we've been working with for a few years. And we started out, did a bunch of work on modeling how they use their vehicles, the routes, the vehicles that were available. And we were able to model that level 2 AC charging would actually be adequate. And there's this tension between, we can do level 2 charging. It's a lot less expensive to put in those chargers and get the utility capacity in versus higher charging DC systems. So it looked like the modeling showed that would work. What it turned out in practice is that between driver behavior, vehicle charging limitations, these were some early buses that actually had thermal regulation issues even under level 2 charging, and also a lot of phantom power loss. So this was a lot of early technology issues. And it turned out the level 2 charging was really borderline for being able to charge those vehicles and get them on the routes that they needed to be on. So our response to that was to work with new chargers. We brought in some newer chargers, but they're low power level 3 DC chargers. So much faster charging, 2x, 3x, but we don't have the big inverter cages and not nearly the demand on the utility. So there was much less utility interaction for this. And we're working with vehicle manufacturers too. So one of the responses was to work with this manufacturer on the charging limitations we were seeing and those phantom loads. So it's an early market, and we end up working with all aspects of this. Another quick case study this is a California school district, and we were well through the design of this program. The engineering showed that we needed a 400 amp service total for the EV charging. We were able to convince the utility to go to 600 amps for us due to future loads. And once we were off and running on this whole thing, the customer came to us and said, "Hey, guess what? We just got 7 new buses," literally out of the blue. So those 7 new buses actually require a lot more than 600 amps when we put the entire load together. So what we were able to do is, working with Mobility House, we're using their charge management system to manage the level of charging on those buses so that we don't go beyond the 600 amp service and switchgear that we have capacity for today. And so that allowed the district to bring in these new buses, charge them, and still be successful with that program. Okay, the last thing I'm going to talk about really quickly are some of the financing structures that we're seeing out there. The current trends, this is kind of interesting, is that we see mostly ownership. And the reason for that, so clients are actually buying these things. And the reason for that is that the way the incentives are structured right now, the end customer can actually get directly to those incentives and sometimes can easier get to those incentives and gets more benefit directly from them. So we see that now. We see a lot of ownership now. We think that that's going to be transitioning to third-party ownership models and as the incentive scenarios change. And we're also seeing EV charging and DERs often actually financed separately, or the structure of the finance is different. And I'll talk about that right here, which is, so financing types for the EV piece of it, those first 2 here on the list, charging as a service and transportation as a service, you're probably familiar with, but charging as a service, basically the entire charging, the envelope is put together in one service. And so the chargers, the CMS or the CPO provider, the billing, all of that is bundled together. And you pay, one fee basically for doing that charging. Transportation as a service is very similar to that, but we add the vehicles to that so that the vehicle price is bundled into that. And oftentimes even the drivers for that. So for the DER side, those kinds of service or those kind of financings don't really apply as easily. And so for solar PV, the standard third-party financing has been power purchase agreements. We also see that in times you can bundle a battery energy storage system into that power purchase agreement. oftentimes that's not the best outcome or the best way to share risk. So for battery energy storage systems, we often see even a third kind of financing on these projects where it's either done under a lease or a shared savings, some sort of tolling agreement. And so the financing of these things, when you're combining EVs and DERs, can be fairly complicated as well. And each one of those different financing requires a significant analysis and negotiation. Okay, so that's it for me today. I'm going to stop sharing my screen and hand it over to Maeve.
Okay, great. Thanks, Tom. So thank you for having me today. Thank you, the Mobility House, for hosting this webinar. My name is Maeve Lawniczak. I'm a project manager at AlphaStruxure. And for the past few years, I've primarily been focused on designing and delivering microgrid solutions for a number of our fleet customers. So I'm looking forward to sharing a few of the projects that we've been working on lately. So just a little bit about AlphaStruxure. AlphaStruxure, we are an energy as a service company. We're a joint venture company between the Carlyle Group and Schneider Electric. And so Carlyle brings the capital backing to all of our projects, and then Schneider Electric brings the microgrid and switchgear and metering technologies into all of our projects. We design, finance, build, own, operate, and maintain the energy infrastructure solutions that we provide. So we work closely with the client from as early as the conceptual design, and then we deliver a turnkey solution, and we will operate and maintain the system that we've provided for the client for 20 to 30 years, the duration of the contract. And so we've got a number of projects either in being constructed or that have finished construction, which I'm sharing here. The first one is our JFK Airport New Terminal 1 project. So this is in construction. When it's completed, it will be a little bit over an 11 megawatt microgrid system. It will have the largest rooftop solar array in New York City. And one of the key benefits for the client on this project is the long-term cost predictability that the energy as a service solution will provide. And the two projects that I'll focus on today are the MTOC, which stands for Equipment Maintenance and Transit Operations Center, located in Montgomery County, Maryland. And it will, when it's finished being constructed, it will be a 7 megawatt microgrid system in total. It will provide energy to an electrolyzer, and which will provide the green hydrogen to power their fuel cell electric bus fleet. And one of the key benefits here for the client on this particular project was the sustainability value add. And then the final project was completed in fall of 2022. This is a 6.5 megawatt microgrid system. It provides resilient energy for a battery electric bus fleet of 70 buses. And the key benefit to the client for this particular project is the resilience value add. And so just focusing in on the Montgomery County projects that we've been working on. Montgomery County in general, it's north of Washington, D.C. It is the most populated county in Maryland. The county itself has been proponents of microgrids for a number of years now. Previous to the installation of the two microgrids shown on this slide, the county actually had installed 3 other microgrid systems. So they've been advocates of this type of a solution for a while now. So just a few stats about each of the microgrid solutions. So the first one, the MTOC microgrid, as I said a few minutes ago, we broke ground for this project just earlier this month. It will ultimately support a fleet of 200 buses, and that will be a mixed fleet of both battery electric buses and fuel cell electric buses. And it's located in Brookville, Maryland. The second depot, which has been operational since fall 2022, will ultimately support a fully battery electric bus fleet of 135 vehicles and is located in Silver Spring, Maryland. And so just to dig in a little more on the MTOC site, this is, I believe it's a little under a 15-acre site, so it's a fairly large depot. The depot itself was constructed in 2012, so it's also fairly new. When everything's said and done, we'll install around 5.65 megawatts DC of solar canopy. The solar structures are 17 feet tall, and that requirement is due to the ability for a tow truck to be able to pull a transit bus out from under the canopy. And so that's what dictated the height of the canopy system. There's also a 2 megawatt, 7.3 megawatt hour battery energy storage system. And so those two distributed energy resources will work together, and any excess solar that's generated during the day will be dumped into the battery system. And then that battery energy storage system will be dispatched at night to facilitate their existing CNG refueling load, and then transition into supplying energy for their hydrogen electrolyzer once that's installed. As I mentioned, this will be a mixed fleet, so there will also be battery electric buses located at this site. So we are also installing a little under 2.5 megawatts of chargers. It's a mix of 180 kilowatt chargers, which have 3 dispensers each, and then a number of high power chargers that will have mechanical pantograph arms. There will be a 1 megawatt hydrogen electrolyzer, and this will provide enough hydrogen for their first 13 fuel cell electric buses. And the county also has 2 existing 725 kilowatt backup generators that currently can only support one of the buildings that they have on site. And so we're tying that system into our microgrid so that it can support the cumulative load in the event of an outage. And just for perspective of the project vendors, in general, AlphaStruxure, we are technology agnostic, and we figure out the right project partners and vendors to work with. We customize that specific to the client and to the project itself. So for the MTOC project, the EPC firm is Mortensen, our engineer of record is WSP, and then the technology vendors are listed on this particular slide. So we are leveraging SMA inverters, SunPower's Maxion 485 watt solar panels, Heliox chargers. We also have a number of power chargers for passenger vehicles, and shunt for the mechanical arms for the pantograph. And of course, we're also working with the Mobility House, who is providing the charge management controller as well as the charge management software. And then Schneider Electric, our joint venture company, they provide the hardware for the microgrid controller as well as the software applications that optimize the dispatch of the distributed energy resources located on site. And the entire system is monitored by AlphaStruxure's Integrate solution, which houses Aviva. So we're able to monitor the site from our network operating center and monitor, any issues, maintenance, et cetera. And the second case study is the Brookville Smart Energy Bus Depot. This particular project has 2 megawatts of solar canopy, a 4 megawatt hour battery energy storage system. For both projects, The utility that we worked with was Pepco, and for this particular project, we actually collaborated with Pepco, and they are performing a pilot project with our battery system. So they will be able to leverage the battery at Brookville up to 10 times per year when they need it. And this gives them the ability to better understand how large battery energy storage systems can support their system. As I mentioned earlier, the Brookville Depot is housing all battery electric buses. And so there's only charging, no hydrogen at this site. And so there's a little over 4 megawatts of charging capacity at this site. We work with Heliox on this project as well. There's also 3 633 kilowatt natural gas generators at the site. These generators have the ability to run on natural gas, renewable natural gas, and can take up to a percentage threshold of hydrogen as well. And these generators were installed to provide an infinite amount of resilience in the event of a grid outage. And just a kind of a peek into our process. So for the deployment of the Brookville Bus Depot, ultimately the project itself was constructed in about 1 year. There was over, I believe it was a 25 or 28 stage construction process. So the depot itself maintained 100% operation capabilities throughout that year of construction. There were 56,000 labor hours, and out of all of those labor hours, 0 safety incidents occurred. So we're very proud of those stats. In terms of our process, so again, we were worked with the county, very early on, and they didn't know exactly all of the details, but they knew they wanted a microgrid that could provide full resilience to their future battery electric bus fleet. And so just starting with that mindset, we worked with them to understand, is solar a good fit here? Is battery energy storage a good fit here? The right DERs, the size of the DERs, the number of chargers, etc. So we did an extensive amount of modeling with them, and shared with them different scenarios, gave them options all along the way to choose from, and highlighted the advantages and disadvantages of various scenarios. From a pre-construction standpoint, we walked through the construction sequencing plan with them. And so we all sat together, their operations team, their leadership team, our team, went through the construction sequencing plan, and had the opportunity to discuss and, highlight any issues, and reiterate and improve the sequencing plan, which, as I mentioned earlier, ultimately led to, very successful implementation of the system. After everything was constructed, there's a rather complex commissioning process that occurs. So we had 82 commissioning use cases. So, figuring out a number of different ways to model the DERs interacting with each other, as well as the utility, and making sure the system, works as it should. And then now we're currently in the operation stage, and we will do that for the duration of the project for the next 25 years. And then my last slide, this is just kind of fun. I remember early on when I started on the Brookville Bus Depot project, when I would look up the site on Google Maps, this is always what I saw. Obviously no solar panels at that time, but if you Google the site today, you can see our full system implemented. So that's always fun to see. And that is the end of my presentation.
Thank you, Maeve. I'm going to turn on the Q&A section. So we have a question, and it says, is self-consumption always the best configuration for an on-site solar with EVs?
The real world is complex, and there could be a bunch of different, corner cases that would cause you not to want to do self-consumption. For example, you might have a very strong tariff that encourages not to do self-consumption, or you may have a project like Tom and Maeve described, where instead of like immediate self-consumption, you might want to do delayed self-consumption, where that solar feeds the battery energy storage system first. But in general, you're going to, if you have something and create something yourself, that's going to be cheaper than if you buy it directly and then try to sell it back to the organization that sold it to you.
Our next question is, how do you manage network loss issues?
So you have to be really intentional when you're setting up a communication architecture. Earlier on, I mentioned that an API would be fine for sites, for integrations that weren't for critical power functionality. I always recommend that you go with a hardwired solution to have two devices talk to each other. I also think having that intelligence on site, whether it be any of the intelligences and any of the DERs, or a local controller-based CMS, or a physical present microgrid controller, also helps with those latency and loss concerns.
Thank you. Someone has a question for Maeve. How did your team determine the quality of energy you are going to get from solar? And maybe the levels?
Yeah, or maybe the quantity of solar. In terms of how we size the solar, and apologies if that isn't the question. So at both sites, Pepco's the utility, and they do have net metering. The county specifically could leverage aggregate net metering. So right away, the county knew they want to, if there's space on the site, they want to hit that 2 megawatt limit, which we did at Brookville. We covered as much square footage as we can. There really wasn't any more space to add solar than where we did. MTalk, obviously, it was a much bigger site, so we had the square footage to add the solar. However, we still have the 2 megawatt net metering limit. So even though we've got a 5.65 megawatt solar array on site, we'll always be limited to, we'll never be able to push more than 2 megawatts back onto the grid, which influenced how we size the battery energy storage at that particular site.
Thank you. I think this question also might piggyback off of that. How did your team determine the value of solar energy collected, and further about selling it to the grid for these facilities?
From a net metering standpoint, so that is the revenue generated back to the county, that's dictated by Pepco, and something predetermined. I think it's a 1-for-1.
Okay, we have one more question, is what was the original timeline from beginning to end, and what was the actual timeline? Were there, major bumps along the way?
Let's see. So for Brookville, the project, we started the design actually March 2020. So right when COVID happened, and given the global pandemic, really one of the challenging aspects of implementing the project early on was just the EV market was still pretty new. Chargers were still new. So we worked with Hughes, and they obviously had a number of installations in Europe. Same with the mobility house. Everybody had a significant presence in Europe, and we're coming into North America. And so as a group, we were all still kind of navigating the nuances coming over to the States. I remember one time I received a installation manual in German. So that's just one example of some of the challenges that we had early in the design of the project. From an implementation standpoint, luckily we were able to stay on track. The project was actually originally planned to be implemented in 3 stages. And everything went so well in the first stage or the first phase that the county requested that we accelerate the build out of the system. And so we actually finished it, I guess, ahead of time than originally planned. And then MTalk, we just broke ground. So knock on wood, but hopefully everything stays on time. We're expecting to be finished with construction September of next year.
Fantastic. There's some really great photos of that as well. We have a couple of more questions that have come in. Is it common to change the depot location based on permitting, grid interconnection, or do you usually install at a customer's existing depot?
My experience has been a little bit of both. So it's typical to, I think for larger installations in our experience, we've used the existing depot. And as Maeve was talking about, there's the challenge of actually building this out. And oftentimes the vehicles actually move through the depot differently. And keeping the existing functionality in place while you're building this out is a real challenge. Another issue we've run into is just utility capacity for enough charging just for the build out. And generally moving the depots, unless our customer has had other, basically land that's in a good place, that has good utility distribution access. Those are the kind of things that we go through and look at. Is it more expensive to build out a new one, or do we try to work within the existing confines?
Sorry, we have another question. How do you determine the number of required chargers for the fleets? Is there a generalized ratio for vehicles to chargers you've observed in projects? And also, how do you determine the types of chargers? Elizabeth, you might be able to answer this one.
Yeah, so I think it's important first to make the distinction between chargers and dispensers, as oftentimes those numbers can be different because there can be multi-dispenser units. I always encourage there to be an equal number of dispenser to vehicle ratio, if possible, given physical site constraints, as we can remove a lot of the electrical constraints through an automated load management system or through additional DERs. And so then the math starts really working differently, and that frees up, the fleet not having to worry about physically moving and pulling in and out their vehicles. But of course, that's not always realistic. And so you want to try to get as close to that one-on-one as possible. And you want to really take a close eye on the fleet's duty cycle. How many vehicles at any one given time at max are going to be in the parking spot? And then, of course, you can do all sorts of various different plannings and assumptions to figure out how does the rate of my charger affect how much power it's going to get. A note, a good charge management system will make it so that the chargers don't have to always charge at their max rate, and so that you can really modulate the flow of power. And so maybe having a higher powered system gives you more flexibility. But of course, for that greater flexibility, you're going to also pay more for that charger. So really, it's a trade-off in what your duty cycle shows.
All right, we have a slightly more complicated question. Can you shed any light on contingency planning for the scenario of net metering going away or shifting to time of use dynamic type tariffs? How does this play into the ROI calculations for these types of projects?
I can take a shot at that one because we're doing that every day. So in California, for instance, net metering is grandfathered. So, when you're doing your project planning and design, you want to be working within the grandfathering constraints and then modeling to those. What does it mean for net metering going away? It depends on where you are, and it can be difficult to anticipate. Generally speaking, what we're seeing with trends for net metering going away is that the avoided cost of energy is kind of used as the export value. So this is where the state of California again and other states have gone when moving away from net energy metering, in that avoided cost of energy is basically, it's pretty close to the wholesale value of energy. So we see a significant drop off in exported energy value. And so that, since it's exported energy that is primarily affected when you move away from net energy metering, there are a couple of different ways to address that. One is to downsize the system significantly so that you don't have much export. And the other one is to store or use that energy on site when it's being generated, so you don't export it. So if you can, in the case of integrating DERs with EVs, we want to see if we can get our dwell times during the day with solar PV so that we can use the vehicles as the batteries. Otherwise, putting in stationary batteries to help manage that export can sometimes be good. There's the battery equation we see often is not tremendously financially compelling by itself. And one of the things that you need to look at there is that there are often other value streams that you can get into working with your local utility. And again, there are issues depending on whether you're in front of the meter, behind the meter. But it's a complex thing that needs to be looked at and exactly where you are.
Thank you. We have two more questions there, I think directed for Maeve. So how many more microgrids in Maryland are you planning and are in the future with AlphaStruxure?
We are always, as a partner with Montgomery County, helping them look at different sites and evaluate kind of what the advantages might be of a microgrid. So there's nothing set in stone as of yet, but obviously Montgomery County is super progressive county and definitely sees the value of sustainable, resilient energy. And we're ready for the next one when that opportunity comes around. So more to come on that.
And then the next question was for both Montgomery County projects. Is there an expected break-even date? If that is beyond BESS expected lifetime, is it a replacement included as the future investment?
Yes, so that's packed into the energy as a service cost. So for the MTOC project specifically, that's a 25-year contract. I believe like inverters, chargers, the battery energy storage system, they have a lifetime somewhere between 10 to 15 years, depending on the technology, but we have embedded replacement costs into the offer, and we'll do that replacement, at that time.
And I have one more question. What are the key challenges faced by microgrids in transitioning from traditional energy sources to renewable energy systems?
I think overall it can feel a little overwhelming at first, like when you're so used to a client, so used to working with the utility to get their power, maybe not even having to rely on power at all. For fleets specifically, obviously, they're more used to relying on a fuel source. And so just helping the client navigate and get familiar with different energy solutions that could benefit them and figure out the sizing and where it can go. I think footprint is also kind of a nerve-wracking topic with fleets specifically too, because parking is key for them. And so I think that's also a focus of DERs, is how do you add DERs to a site and use the smallest amount of space possible. And so that also can require some creativity.
I'd like to add just a little bit to that as well. I think there are two other things that we run up against immediately on these things, which is cost. And generally speaking, if you're looking at solar plus storage, it's not as cost effective as standard fossil fuel generation as backup. which is, I think, why you see in Maeve's examples a large natural gas fired generation in there. And the other part of that is permitting. So we're seeing in a couple of states, I think California is one of the leaders here, where it's getting more challenging to permit fossil fuel generation. And so the states are really pushing to move customers away from that. That's a kind of a balancing act we're beginning to get into that we see in California. Cost versus permitting.
Oh, we have one more. So that's response to Tom. I hope to see net metering continue existing and come back to regions across the globe. It just makes most sense to even the playing field. I also hope we begin to see more VPP pilots that supplement energy production with selling back stored energy to the grid. Well, we are at time, and I want to thank our speakers for being here today, and also thank you for everybody who attended. We record these, we put them up for free on the mobility website and our YouTube. We send everybody an email. It will either go out tomorrow or Monday morning. They'll have the link to the recording, so you can come back, refer to it, share it to other people. Thank you guys again.
Thank you, Sam. Thank you, everyone.
Thank you so much.
Yep.